Good morning and welcome back to classes. I hope that you had a lovely Easter weekend and that you were able to enjoy it to some degree, hopefully with some family members, even if it was just the ones that you're currently co-quarantining with. In any case, we are ready to start a new chapter. We are starting chapter 8 this week. It is a short one. It will only require today's lecture and Wednesday's lecture, and then we'll be back to taking another test on Friday, immediately post our live meeting like we did last week. So it is a short chapter, and it will probably feel like a short week. Anyways, I hope that it does. In other news, the grades for the test that you took last Friday, you should have up on Blackboard by this evening, or at the latest, by tomorrow. So those should be forthcoming shortly. All right, let us go ahead and get started. I am going to go ahead and put up the notes for today so that we can get started. All right, so I'm going to start sharing my screen here. There we go. All righty. And as you can see, we are starting chapter 8. Chapter 8, we are going to be discussing integers. Integers is how we talk about the set of numbers that includes positive and negatives. As you can see here, right from our definition, as we start section 8.1, integers are defined as the set of all positive and negative numbers on either side of 0. And 0 is neither positive nor negative, okay? And, I'm so sorry, I don't know why this is happening again. I'm telling you, I gotta figure out how to get more sleep. Anyways, if you think of 0 on the number line, it would be in the middle, and you'd have all positive numbers going on to infinity on the right side of 0, and all negative numbers going on into infinity on the left side of 0. So let's talk about a few vocabulary terms that you should be familiar with as we increase our discussion of integers. The first term that you should be aware of is zero pair. Zero pair is the same number, both positive and negative, and when added together, they make a 0, and that's why they're called a zero pair. Sometimes we refer to these as the inverse of each other, and you will see when we get to a little later in the notes where we're going to have that conversation. But your textbook also refers to them as a zero pair, so you should be aware of both terms. Here's an example of a zero pair. You have a -1 plus a +1 together make a 0, so the -1 and the +1 are considered a zero pair. And these little symbols down here are just to allow you to follow through what sign that particular integer has. Here's another example, a +2 and a -2 together when they are added equal a zero pair. Oh, excuse me. We also have two models that we use to explore positive and negative numbers, and here they are. We use what's called a measurement model, which you may have seen referenced as an integer number line, and that's what I was referring to earlier. Here's where we have a number line where 0 is in the middle. It is neither positive nor negative. Everything on the right of 0 is positive. Everything on the left of 0 is negative. And so therefore you've got a -1 here, okay? And if we look at this example, we can, on this number line, this measurement model, show that -1 plus 1, okay, is indeed a zero pair, because the first number, as we read this expression from left to right, is where we start on the number line. So -1, we start at -1. The symbol, whether plus or minus, tells us in which direction to move along the number line. So if it says plus, we're going to move to the right in the plus direction on the number line. If it should say minus, we would move to the left in the minus direction of the number line. And then the last number, the second number, tells you how many units to move in the direction that the symbol told you to go in. So here, because we're going in the plus direction, we're going to be moving in the direction to the right. This last number tells you to move one place. So if we start at -1 and we move in the plus direction 1 unit, we land at 0. So indeed, a -1 plus 1 unit in the positive direction takes us to 0, making -1 and a +1 a 0 pair, just as we showed earlier. But here we can show that on the number line using a measurement model, okay? We also have what is called a set model, or sometimes called the chip method, where, for example, if we're talking about a +3, we have 3 positive chips, okay? And a -3 would be represented by 3 negative chips. Your textbook calls the positives black chips and the negatives red chips. I have positive pink chips and negative purple chips. So it's neither here nor there. But if I have 3 positive chips and I have 3 negative chips, you can see how each positive cancels out a negative. So if this positive cancels out that negative, and this positive cancels out that negative, and this positive cancels out that negative, the sum total of what I have is 0. So again, proving that a +3 and a -3 are a 0 pair, because when put together, they make a 0, okay? So these are 2 ways that we can explain how positive and negative numbers work together when we're adding them, using both a measurement model, which is this number line, or a chip model, which is this diagram that you see here. Now let's just talk about the rules and regulations for addition. This is the more complicated of all the operations that we are going to perform using integers. Addition is the one that has the most specific set of rules. So it's why we start there first, okay? Now, you need to recall when discussing addition that addition means to put together or to form a union of 2 disjointed sets. So that's what we're going to do, okay? And we're going to start by using set model. So let's say that the example you were given was 12 plus 7 plus a -6 plus 8 plus 13 plus a -1. What would be the answer to this expression? We can use a set model to help us find the answer, where once again, we have one set of all the positive integers and one set of all the negative integers, and then we simply add up how many chips there are there. Here we have 12, 7, 8, and 13. So if we add all those chips together, we have 40 positive chips. Over here we have -6 and a -1. If we add all those chips together, we have a total of 7 negative chips. And then if we put those 2 sets together, forming a union, 40 positive chips plus 7 negative chips equals a sum total of 33. And one of the first basic rules that drops out of this example is that when adding integers, if they have the same sign, you just add them together and keep that sign. So we added all the positive chips together and we got a total of 40 and we kept the positive sign. We added all the negative chips together, we got a total of 7 and we kept the negative sign. And that is the first basic rule of adding integers, and that is that you add, when they have the same signs together, you add them together and you keep the sign, okay? Now here, we had a positive and a negative. They have a different rule, which you're going to see now in our example of the measurement method, okay? So if we're using the measurement method as a way to model our addition of integers. And let's say that the problem that we're going to solve here is 3 plus 1 minus 6 plus 8 minus 12. When using the measurement method, we are going to read this from left to right, and we're going to do it in small pieces. So the first piece we're going to do is piece A, which is 3 plus 1. Okay, so here's 3 plus 1. On the measurement model, this would be where we start. This is the direction we're moving in. This is how many units we're going to move. So we're going to start at 3. We're going to move 1 unit, and that makes us land at 4. So we can see from the measurement model that 3 plus 1 equals 4. Okay? Now we're at 4, and we're ready to move on to the next section, which is B. So having left off at 4, now we're moving on to minus 6 right here. 4 minus 6. Okay, using the measurement model, we start at 4. Remember, we always read from left to right. We start at 4. We are going to move in the negative direction, and we're going to move 6 units in the negative direction. So we start at 4, move in the negative direction, 6 units. If we move that, we have 1, 2, 3, 4, 5, 6. Where do we land? At negative 2. So that we know that 4 minus 6 is negative 2. Here we have it. Therefore, 4 minus 6, or another way to write that is 4 plus a negative 6. We're going to talk about why we can write it that way in a little bit, equals a negative 2. Now, what you need to notice is that they showed 4 minus 6 equals a negative 2 is not the same as 6 minus 4 equals 2, but we're keeping the sign of the negative number. And in a little bit, we're going to see what that rule drops out at. Just like we saw the first basic rule drop out of our set model example, we're going to see that another basic rule drops out of this measurement method example. Okay? So now we are at a negative 2, and we're ready to move on to part C, which is where we're going from the negative 2 we just landed on and adding 8. So that here it is, part C, negative 2 plus 8. Okay, again, we're starting at negative 2, moving in the positive direction, 8 units. So we're going to go ahead and do that on our measurement model. Here is negative 2. Moving in the plus direction, 8 units, 1, 2, 3, 4, 5, 6, 7, 8, and that lands us at positive 6. Therefore, we know that negative 2 plus 8 equals 6. Or if we were to turn that around, 8 minus 2 is 6, and we kept the positive sign. Let's see if you can notice the pattern as to why we're keeping the sign that we're keeping. Finally, now that we're at positive 6, here, we're ready to move on to the last portion of this expression, which is minus 12. We're at a positive 6, minus 12. So sure enough, part D is 6 minus 12. We're starting at a positive 6, and we're going to move in the negative direction, 12 units. So we're going to start at a positive 6, move in the negative direction, 12 units, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, and we land at a negative 6. Therefore, we can say that 6 minus 12, or again, we can write that as 6 plus a negative 12, which we'll discuss in detail in a little bit, equals a negative 6. Please note that this is the same as saying 12 minus 6 equals 6, keeping the negative sign. Now you'll note that every single time that we kept the sign, I wrote a little note here saying sign of the bigger number. Okay? So whenever we were adding together, as you saw in the second example, two numbers that did not have the same sign, we did the subtraction of the bigger number minus the smaller number, and then whatever we got as an answer, we kept the sign of the bigger number. Here in 6 plus a negative 12, 12 was the bigger number, so we kept the negative sign. Okay, over here, all right, in 8 minus 2, 8 is the bigger number, and it was positive, so we kept the positive sign. And there you have it. That is the second basic rule that drops out. When we are adding integers, the second basic rule is when signs are different, you always subtract the smaller number from the larger number, and you keep the sign of the larger number in your answer. So those are the two basic rules of how we add integers. We keep same signs, we just add them and keep the sign. When the signs are different, meaning one integer is positive and the other integer is negative, we subtract the smaller number from the larger number, and we keep the larger number's sign in our answer, as you saw in these examples above. Now, if you want to have a more detailed breakdown, these two basic rules I gave you encapsulate all the very small specific rules, but if you want to see them all, you can see them at the top of page 309 in an orange box. They break down each of the individual rules, but it basically comes down to these two basic ones that I've mentioned. If the signs are the same, add them and keep the sign. If the signs are different, subtract the smaller from the larger and keep the sign of the larger number. Those two are the big umbrellas wherein all the smaller detailed rules fall into, but you can see them all specifically laid out at the top of page 309 in that orange box, if you'd like to look at them. Now let's talk about some properties of adding integers, okay? Property number one, when adding integers, we have closure property, which if you recall from chapter 7, the closure property tells you that if A is an integer and B is an integer, then A plus B will equal C, which will also be an integer. So if we are adding integers, our answer will be an integer, okay? Then we also have the commutative property, which is always in effect whenever we are adding. And the commutative property says that if A and B are integers, then A plus B equals the same as B plus A. And you know this to be true with regular addition. It is also true when using integers. For example, a -2 plus 1 gives us a -1. And a 1 plus a -2 also gives us a -1, okay? So please note, once again, I'm highlighting this. In a minute, you're going to find out what this is actually called. But please note that 1 plus a -2 can also be written as 1 minus 2, and they mean the same thing. So in a minute, you're going to find out what that is officially called. But I keep highlighting this because it is an important concept for you to notice. All right. The third property we want to talk about is the associative property for integer addition. Again, because we're doing addition, addition inherently has an associative property. The associative property says that if A and B and C are all integers, then we can either group them as quantity of A plus B first and then add C, or we can group them as A plus the quantity of B plus C. Either way, we will still get the same answer. So the grouping, the way we group them or associate our integers does not change the sum total. As you can see in this example, we have -2 plus 1 plus 3. We've grouped -2 plus 1 first, which gives us a -1. Now we add the +3, we still get the sum total of a +2. If we chose to do -2 plus and group the 1 plus 3 first, which would give us a 4. And then we'd have a -2 plus 4, the sum total would still be a +2. So regardless of how we group the integers, we still get the same answer, okay? Now, moving on to property number 4, the identity property of addition. This is still the same identity property that we saw earlier when discussing addition, and that is that 0 is a unique integer such that when you add 0 to any integer, you still have that integer. So A plus 0 will still be A, and even if we switch it, because addition has commutative properties, 0 plus A will still also be A. For all integers A, where A is an integer. So any integer that we put in for A, if we add 0 to it, we will still have that same integer. If we start at 0 and we add an integer to it, we will still have that integer, because 0 does not change what we're talking about. So therefore, it is the identity of addition, and it still applies to integer addition, okay? As you can see here, 1 plus 0 is still 1, and 0 plus 5 is still 5. So again, we see the properties, the identity property at work here, okay? Last but not least, we have the additive inverse property for addition. And this is where we explain all those little notes and highlights that I've done so far, okay? The additive inverse property for addition is defined as, for each unique integer a, there is a unique inverse negative a, such that a plus negative a will make a 0 pair. We talked about it when we were doing 0 pairs. I mentioned it when I showed you the measurement model of adding integers, where we saw when we were adding integers of different signs. This is basically the situation. We have an additive inverse. Because we have an additive inverse, we can write this as 3 minus 3 equals 0, or we can write it using the additive inverse, 3 plus a negative 3 is 0. So this is what allows us to write 3 minus 3. Instead of writing it as a subtraction, we can write it as an addition, 3 plus a negative 3. Okay, that is the additive inverse property. And that's what allows us to write those two statements in these two ways and still be talking about the same operation and same quantity. All right, let's do some applications of what we've learned so far, in particular, the applications of the additive inverse, okay? We call it using additive cancellation. So for example, if I am adding quantity A plus C plus a negative C, and then I'm adding quantity B plus C plus a negative C, I can use the additive cancellation where I'm going to use the inverse so that they become a 0 pair and therefore drop out, right? I can do that on both sides. They drop out and now have A plus C equals B plus C. If I once again use the additive inverse to get rid of the C on both sides, I end up having A plus 0 equals B plus 0, right? Because C plus a negative C, the additive inverse adds to a 0 pair, which then basically means I have A is equal to B, okay? So this is how we can do additive cancellation, and we use the additive inverse to help us solve. Now, you'll note that subtraction has not been mentioned to this point, and that's because we use the additive inverse. So we never really subtract, we only add. Same as when we were talking about fractions, where we never really divide fractions, we just multiply by the inverse. The same is true when we're talking about subtraction. We use the additive inverse and then just follow addition rules. So for example, instead of doing 3 minus 10, I just use the additive inverse and write that as 3 plus a negative 10. And now I'm following the rules for addition of integers, which tell me that because these two have different signs, I'm going to subtract the smaller from the larger. So 10 minus 3 is 7. And I'm going to keep the sign of the bigger number. 10 was the bigger number and it was negative, so my answer will be negative 7. Okay? Same thing here. If I've got 7 minus a negative 3, if I use the additive inverse, this is really 7 plus, and what is the inverse of a negative 3? A positive 3. So 7 minus a negative 3 is really 7 plus 3, and that's 10. If you want to think of it as, remember when we were doing fractions, we thought of it as keep, change, flip. Keep the first number, change the multiplication, use the inverse, or flip to the inverse. You can think of this as keep, change, inverse. Keep the first number, change to addition, give the additive inverse of the second number, and then you can just use addition rules. And with that, ladies and gentlemen, we have completed section 8.1. Your homework for this section is going to be found on page 314 to page 315. You'll be doing numbers 1 through 17, except do not do number 6, number 13, and number 15. And if it's got multiple parts, parts A through C only where applicable. Homework will be due before our regularly scheduled class time, which is 1 o'clock on Wednesday. But please remember that we're not having a live class on Wednesday. You will have another video and notes and homework link to work with on Wednesday. I hope you have a wonderful day. Enjoy doing your homework as much as you possibly can. And always feel free to reach out and ask me for anything should you have any questions. All right, I'm going to go ahead and stop sharing my screen here. And I will see you in the next video lecture on Wednesday.